Hello, my name is Jaden Finney, and this is my second physics lab video titled Motion of a Fallen Object. So, the purpose of this lab is to observe an object's free falling due to a force of gravity and also a force of drag. This concept comes from Newton's second law, where the momentum principle expresses the existence of a net force on a system causing a change of momentum over time. All right, so the two forces acting on a free-falling object on are Earth's acceleration due to gravity, or Fg equals mg, mass times gravity, or 9.8 meters per second squared, and the drag force. This is later to be proven in the results of this lab. Due to the momentum principle, the F net force divided by the object's mass causes a downward acceleration of the object as it falls to the ground. The force of drag exists in the experiment because there is always air resistance present on Earth. The drag force exists as Fd equals negative b, which is the drag coefficient, times v squared, velocity squared, times v hat. Cool. So for the experiment, a baseball cap was dropped by hand from an initial velocity of 0 meters per second from 1.83 meters, or about 6 feet. The mass of the baseball cap was approximately 0.085 kilograms. The starting observation time was t equals 0 seconds, and it took approximately 0.7 seconds for the cap to reach the ground. The baseball cap was specifically chosen due to its design. It can catch drag much easier than other objects such as a rock or a boulder, allowing for the experiment to be exaggerated, so it's better to observe. All right, so this is a video right here of us briefly dropping the object. That is the hat at the top. That tan hat is going to fall 1.83 meters down to the floor.
¿Qué color es la camisa?
That was good. Boom. And just like that, falls nice and smooth. That was about 0.7 seconds.
¿Qué color es la
Over
camisa?
here, this other side is my tracker info. So I did about 21 tracked positions for this. I started at the origin at the very top of the hat and just calculated it. I had a little distance stick for 1.3 meters. And overall, it was a pretty straight drop, not too much curvature in the x direction. So this is my code. So I have two lines of code, or two sets of code for this. One is for drag coefficient of 0. The other is our calculated drag force, which is found to be b equals 0.062. All right. And for these results over here, this is all three of the lines being coded into GlowScript. So we have three lines over here. The orange line is the simulated ball or hat being drawn from 1.3 meters with the inclusion of drag with the 0.062 drag coefficient. The gray line represents the hat being dropped from absence of drag in GlowScript, and the blue line is the real life observed motion. And overall, you can see here, all three have a very similar trend. There's they start off really slow in their position, then they get acceleration faster, so they drop quicker to the ground, as caused by the F net force as shown in the momentum principle. Overall, though, the graph with the absence of drag, the gray one, falls much faster than the other two, followed by the inclusive drag, the simulated one, in GlowScript, and then surprisingly, the observed motion one found to be the slowest. All right, so discussion. What if the object was initially thrown downward, the terminal velocity in this case would be the same as the original, because the force of gravity does not change, and the force of drag is only dependent on the velocity for a given object. The terminal velocity would only be reached quicker. So what does this mean? Out of those three graphs that I've shown, the graph of the inclusion of drag, the gray one, represents terminal velocity because the drag force is necessary to balance out the gravitational force. All right, and so in short, with the inclusion of air resistance, an object free falling on Earth will accelerate downward due to the momentum principle. The F net force is the sum of the force of gravity and the drag force, which after a certain period of time, a terminal velocity will be reached. To improve the procedure for a future experiment, minimizing the chances for the object to shift in the x direction while it's free falling is essential. Additionally, making sure the initial velocity is absolutely 0 meters per second in case like hand movement at all at the beginning, or like it starts at a velocity that should not be 0. Thank you for watching my video. You guys have a great one.